When we simplify expressions with rational exponents, we follow the same fundamental rules that we followed way back in Algebra 1 when we simplified any expressions that involved exponents. We're going to look for our final simplified versions to not include any parentheses, to have no situations where a power is raised to another power. We're going to want to see each base only once, and we do not want any negative or zero exponents to appear in our final expression. So let's try a few examples and make sure that our answers and our final simplified versions follow these four basic rules. So in our first example, we have a multiplication in the numerator followed by a division of the same base. Obviously, this is not the most simplified version. We have three occurrences of the base x that we need to make sure are simplified correctly. We look first at the numerator, where we have two basic base x expressions being multiplied together. Recalling our rules for exponents, that means that we are going to add those two powers together, and we're not going to worry about the denominator just yet. Adding 3/4 and 1/2, we have a common denominator here of 4. So our second fraction is going to turn into 2/4, and we get x to the 5/4 power. Following that with x squared in the denominator, we now have the division of the same base. We're still not done because that base x has appeared twice still. We're going to look at the division of the two and subtract the powers. As the rule suggests, as suggested since Algebra 1, when we have the same base that's being divided with itself, we subtract our powers. So we're going to have x to the 5/4 minus 2, which is x to the 5/4 minus 8/4, which is x to the negative 3/4 power. Now, if we were only to follow a few of our basic rules for simplifying exponents, we would be done. We see one singular base x. We went from there being three of them down to there being just the one, so we feel good about that. But we should be concerned by the very last of our rules, which is that no negative exponents are allowed to appear. I still have x raised to the negative 3/4 power. I remember that that 3/4 power just means reciprocal. So I move that fraction, that fractional rational exponent power and its base to the denominator, change it to being positive, and there's my final simplified version. Two applications of the exponent rules that we already know worked the same way as when they were integers. There's no different work here. We added the numerator powers because we were multiplying the bases together, and we subtracted the denominator because it was being divided away. In this example, we're going to have a similar situation, but before we can do the work, we have to rewrite these expressions so that they have rational exponents, and then they aren't just hanging out there with all of these roots. Our numerator becomes x to the 3/4 power. Our denominator becomes x to the 1/2 power. This is not totally simplified because I have an x in the numerator and the denominator. And similar to what we saw in the last example, we're going to subtract the powers. 3/4 minus 1/2 is just 1/4. Depending upon the instructions of a question, if the question says to leave it with a fractional or rational exponent, this would be a perfectly appropriate answer. But since this is such a simple radical, and it came from an expression that had radicals in it, it is likely that they will ask you to change it back into a single radical expression. In this situation, we're going to look to follow the same rules. Do we only have one occurrence of the base? Or in this case, do we only have one occurrence of the radicand? Did we simplify the powers as much as we could? Which we did. In our next example, we have a power to a power situation. The most common mistake in an example like this is forgetting to apply this 1/2 power on the outside to all of the individual factors of the inside. So 121 will get that 1/2 power. X to the 1/2 will get that 1/2 power, making it 1/4. And y to the negative 3/5 will get that 1/2 power, making it y to the negative 3/10. I'm going to hold off looking at these two for just a second and focus my attention right here. 121 to the 1/2 power is the square root of 121, which gives us 11. X to the 1/4 is going to stay x to the 1/4 in our simplified form, and y to the negative 3/10 is going to move to the denominator and become positive. Because this question started with rational exponents, it is likely that the answer will be requested of you with rational exponents. However, you do have the option, if you're just writing this for yourself, that you can reapply some of that radical work from earlier in the lesson and say that you have two individual radicals that you can use. It is likely that you will leave it in this form. We will see later on in this unit that this is not an ideal situation. We don't like having radicals in the denominator. It makes a lot of the work that we're going to do a lot more challenging if you have a radical in the denominator. So in those situations, it is likely that we will be requested to leave it in the fractional exponent form. In our final example, we have what appears to be a nested doll version of a radical expression. We've got a radical inside of a radical, and we're simply just going to work our way out. The interior of the first radical can be thought of as x to the 1/4 power. That exterior cube root can be thought of as to the 1/3 power. Similar to the last example, if I have a power to a power situation, I can simply multiply the two powers together, and because it started as a radical expression, I'm going to change it back to 1. This is a question that looks significantly more challenging than it actually is. Just remember that when you're working with radicals, you want to try to evaluate from the inside out. In this case, the very last thing that we would handle would be the cube root. I would try to do all of this in here. But then I would have to worry about the 4th root and the interior radicand. Just a note on this example, let's say hypothetically that we gave a similar example where instead of it going 3rd root, 4th root, it went 4th root, 3rd root. In that situation, you would engage in a similar kind of rewrite, and you would end up in the exact same place, the 12th root of x. That's not to say that you should just start interchanging them. That's not what this example is suggesting. This example is suggesting that the commutative power of multiplication allows us to end up in the same place, whether we take the 3rd root of the 4th root or the 4th root of the 3rd root. And because of that commutative property, we would expect that to happen for any roots that we were interested in taking. So just as a recap of what we saw in this video, we were looking for our final responses to not have any parentheses, no powers raised to powers. We want each base to only appear in our answer one time, regardless of how many times it showed up in the original expression. That's not to say we have to get rid of bases. I didn't anticipate x or y disappearing so that there's only one. I only want there to be one x and one y. And then, of course, making sure that we have no negatives or zeros. The zeros are easy. With the exception of 0 to the power of 0, if you're very careful with your powers of 0, they should always turn into 1 or -1, depending if there's a parentheses involved. The -1 is usually where people run into trouble, because they're under this assumption that they've gone through all of this hard work, like in this example, and think that this would be their final answer. We want to make sure we represent that as the division moving to the denominator. And yeah, I mentioned when we did this example, but that this radical in the denominator is not great. But if we're able to represent it at least this way, that is certainly to our advantage, especially if we're going to be doing something else with that expression. So anytime we run into that negative exponent situation, make sure that they get moved to the denominator, similar to what we saw in this first example. So hopefully you got a taste of what this could look like for all of the different properties, using the different properties that we already know and are already well established, and using that to simplify expressions that involve rational exponents.